Section: Introduction. In this section, we discuss the complex challenges we face today, such as epidemics and housing shortages, which arise from the interactions of many individuals rather than a single person's actions. To understand these dynamics, we use agent-based models, ABMs, that simulate groups of agents acting and interacting in a virtual environment. ABMs have been valuable in studying various complex systems, including public health, economics, and disaster response. For instance, they have been utilized to assess vaccination strategies during the COVID-19 pandemic, predict housing market crashes, and design evacuation plans for refugees. ABMs are particularly useful for policy analysis because they simulate how individual behaviors interact with environmental factors. However, their practical use has been limited by high computational costs. Recent advancements in deep learning have helped overcome some of these challenges, allowing us to simulate millions of agents more efficiently and calibrate models using diverse data sources. In these advanced ABMs, deep neural networks can model complex environmental dynamics, and sensitivity analysis can be performed to understand how changes in inputs affect outputs. Despite these advancements, a key limitation remains: the agents in ABMs often lack expressiveness and adaptability. Large language models, LLMs, have shown great promise in text-based tasks, leading to the development of LLM-powered agents that can exhibit more human-like behavior. While there has been some progress in using LLM agents for multi-agent simulations, this work has mostly focused on smaller scenarios. To tackle large-scale systems like epidemics or supply chains, we need to simulate millions of agents and design environments that accurately reflect real-world dynamics. In this paper, we introduce AgentTorch, a framework that enables scalable simulation, calibration, and analysis of ABMs with flexible agent designs and fully differentiable environments. We use AgentTorch to evaluate the effectiveness of LLM agents in large-scale ABM research. First, we investigate if LLM agents can replicate population-level behavior statistics. Next, we propose the idea of an LLM archetype, which groups agents with similar behaviors, allowing us to scale simulations to millions of agents based on LLM outputs. Finally, we compare the simulation accuracy between individual LLM agents and the archetype approach through a case study involving 8.4 million agents representing New York City. Section Summary. In this section, we discuss the challenges of simulating complex systems through agent-based models, ABMs, and introduce AgentTorch, a framework designed to enhance the scalability and adaptability of ABMs by incorporating large language model, LLM, agents. We aim to evaluate the effectiveness of LLM agents in reproducing population-level behaviors and explore the trade-offs between individual agent expressiveness and the use of LLM archetypes for simulating millions of agents. Section: Preliminaries. In this section, we define the tasks involved in simulating, calibrating, and analyzing an agent-based model, ABM. We introduce the necessary notation and definitions to set up our experiments. We also clarify the concept of an LLM agent within an ABM and outline a method for scaling LLM-based agent simulations to larger populations. When we consider an ABM with a number of agents, we represent the state of each agent at a given time as a collection of properties that can change over time. For example, this state might include an agent's age, gender, and health status. As the simulation runs, each agent updates its state by interacting with its neighbors and the environment, both of which can also change over time. We can describe the information an agent receives from another agent during these interactions. In an epidemiological context, this information might represent the spread of an infection. We can express the rules for how agents update their states based on these interactions and the structural parameters of the model, which could include factors like how contagious a virus is or how effective a vaccine is. The environment also evolves based on the agent's actions. The specific functions we choose to define these updates shape the dynamics of the ABM and are often random functions that can be specified through mechanisms or learned from data. To simulate an ABM, we start with initial conditions for the agents and the environment and repeatedly apply the update rules. Although the state space can be very large, we focus on aggregate outcomes over time, which can be represented as a multivariate time series. For instance, in an epidemiological model, we might sum the number of infected agents to track daily infections. Once we establish the functional form of the ABM, we can view the simulation as a stochastic process that repeats for a set number of time steps. A differentiable ABM allows us to compute gradients, which can be useful for calibration. Calibrating an ABM involves finding a set of parameters that make the model's output consistent with real-world data. There are various techniques for this, including Bayesian methods and neural network approaches. We can categorize our analyses of ABMs into three types: retrospective, understanding past events; counterfactual, exploring alternative scenarios; and prospective, designing future policies. This capability makes ABMs valuable for policy design, helping us address the Lucas critique, which argues that historical data cannot predict the effects of new policies. By using expressive agents in our ABMs, we can capture the complex relationships between agent behavior and policy impacts. In traditional ABMs, the rules for how agents update their states are often based on heuristics or theoretical foundations. For example, in an epidemiological model, these rules might be derived from standard equations. However, these rules may not clearly separate the influences of agent behavior from environmental factors. For instance, the basic reproduction number indicates how many new cases one infected person generates, but it doesn't clarify whether a rise in cases is due to more interactions or increased virus infectivity. By incorporating LLMs as agents, we can better separate the dynamics of agent behavior from environmental influences. This involves adjusting the update rules to include outputs from the LLM, which can help us model behaviors like compliance with health policies. We can interpret the LLM's outputs as actions within the ABM, allowing us to ask yes or no questions about agent behaviors, such as whether an agent will choose to isolate at home. Section Summary. In this section, we define the tasks of simulating, calibrating, and analyzing agent-based models, ABMs, introducing relevant notation and the concept of LLM agents to enhance simulations. We also outline the dynamics of agent interactions and the calibration process, emphasizing the potential of ABMs for policy design by capturing causal relationships between agent behavior and environmental factors. Section: Scaling LLM agents for ABMs, LLM archetypes. In this section, we discuss how scaling large language model, LLM, agents can enhance agent-based models, ABMs. To understand complex systems, we often need to simulate all agents to capture important effects that emerge at larger scales. For example, while an individual ant may have limited intelligence, simulating the entire colony reveals how they coordinate, such as using themselves as bridges for others. However, querying the LLM for each agent and action at every time step is impractical. We can simplify this by recognizing that the variety of behaviors is usually much smaller than the number of agents. Instead of querying for each agent, we only need to query for each unique combination of characteristics, which we call archetypes. For instance, if behavior is determined by age and sex, we only need one query for each combination of these traits. For each possible action, we can estimate its probability using a method called Monte Carlo. By estimating the probability for each archetype, we can simulate agent actions by sampling from the appropriate archetype. If we denote the number of archetypes as k and the number of actions as a, we can simulate all agents with k times a queries, which is much smaller than the total number of agents, allowing us to scale simulations to millions. Next, we introduce AgentTorch, a framework designed for creating ABMs with complex dynamics and adaptive behaviors, capable of efficiently simulating large populations. Its key features include: 1. Scalability. AgentTorch uses vectorized computing to simulate millions of agents on standard hardware. For example, it has shown up to 40,000 times faster performance in epidemiological models with 60 million agents compared to traditional frameworks. The use of archetypes helps maintain these performance gains even with LLM-informed agents. 2. Differentiability. AgentTorch offers tools for building differentiable environments, allowing for the calibration of many parameters using diverse datasets. This means we can differentiate through certain functions, enhancing our modeling capabilities. 3. Composability. The framework allows us to combine ABMs with neural networks and LLMs, creating more flexible agent designs. Its differentiable environments ensure that these systems work seamlessly together. AgentTorch also integrates with generative agent frameworks like LangChain. Our work with AgentTorch is driven by collaborations worldwide, with applications ranging from managing a measles outbreak in New Zealand to studying migratory bird behavior in Alaska and analyzing dairy supply chains in the Pacific Islands. Previously, we utilized AgentTorch models during the COVID-19 pandemic to assess immunization strategies across various countries. The project is actively developing, and we encourage exploring our GitHub repository for tutorials, videos, and installation guides. The project website also offers hands-on notebooks for building environments and running simulations. Throughout this paper, we will examine the effectiveness of LLM agents in million-scale ABMs, showcasing benchmark results and code snippets to illustrate how these agents can tackle real-world challenges. Section Summary. In this section, we discuss how AgentTorch enables the simulation of large agent-based models, ABMs, by using archetypes to reduce the number of necessary queries to a language model, allowing for efficient behavior simulation of millions of agents. We highlight AgentTorch's scalability, differentiability, and composability features, which facilitate the integration of complex dynamics and LLM-guided behaviors in real-world applications. Section. Motivating example. COVID-19 pandemic. In this section, we explore the COVID-19 pandemic as a key example to showcase the capabilities of AgentTorch and the usefulness of large language model, LLM, agents in agent-based models, ABMs. The pandemic highlighted the complex interactions between disease spread, social behavior, and government policies, which made it challenging to create effective public health strategies. Human behavior significantly impacted the success of these strategies, emphasizing the need to incorporate these dynamics into our ABM. At the start, we observed a feedback loop where people's mobility affected disease transmission, leading to multiple infection waves. Individuals became more cautious as cases rose but relaxed their behavior when cases fell. Lockdowns aimed at reducing mobility had serious economic repercussions, resulting in high unemployment rates. To address this, governments introduced stimulus payments and financial aid to ease economic strain and promote adherence to health measures. However, these interventions also disrupted the job market and resource distribution for health initiatives. As the pandemic wore on, pandemic fatigue emerged, affecting people's willingness to follow health guidelines, which further impacted both health and the economy. To tackle these issues, we focus on two main aspects of individual behavior: isolation and employment. We aim to understand how these behaviors change based on 1. Demographics like age, gender, location, and income. 2. Disease dynamics, including new case numbers and changes from the previous month. 3. External interventions, such as received stimulus payments. And 4. Internal adaptation, considering the pandemic's duration and its effects on behavior. We prompt agents about their willingness to isolate and work using a specific format that provides context about disease dynamics and demographic susceptibility. We gather data at both census and individual levels for our LLM archetypes and agents. Our experiments focus on New York City, given its diverse population and the significant events from August 2020 to July 2022, which included various disease waves and behavioral changes. We benchmark the performance of LLMs in simulating behaviors that align with observable population trends. We create a synthetic population of 8.4 million agents based on U.S. Census data, each with attributes like age, sex, and location. Our analysis covers the period from December 2020 to March 2021, coinciding with the second round of U.S. stimulus payments. We modify our prompts in 3 ways to assess different scenarios. First, using only demographic data. Second, adding disease dynamics. And third, including information about stimulus payments. For each scenario, we initialize 100 archetypes representing various prompt combinations over the 3 months. We calculate the probability of each archetype performing a specific action, such as going to work, and generate a time series of daily work attendance. We then compare this data with actual labor statistics to evaluate the correlation between our LLM agents' predictions and real-world observations. Our findings indicate that as we provide more contextual information, the correlation improves, suggesting that we can effectively tailor LLM agent behavior. In a second experiment, we assess the ILM's ability to adapt over time, focusing on the period from March to May 2022, after the Omicron wave and a decline in financial support. We modify our prompts to reflect the pandemic's duration and reduced financial incentives, repeating our sampling process. The results, detailed in the appendix, demonstrate that LLM agents can capture behavioral adaptations over time, which is promising for future agent-based modeling applications. Section Summary. In this section, we explore the COVID-19 pandemic as a case study to demonstrate the capabilities of AgentTorch and LLM agents in agent-based modeling, ABM, focusing on how individual behaviors like isolation and employment are influenced by demographics, disease dynamics, and economic interventions. Our experiments, conducted on a synthetic population of 8.4 million agents in New York City, reveal that LLMs can effectively simulate population-wide behaviors and adapt over time, showing high correlation with real-world data as we incorporate more contextual information into their prompts. Section: Benchmarking Agency versus Simulation Scale. In this section, we explore how incorporating agent behavior into agent-based modeling, ABM, affects the balance between agency and simulation scale. We simulate the spread of disease and labor market dynamics in New York City from December 2020 to April 2021, using AgentTorch for initialization. For disease spread, we apply a standard epidemiological model where the chance of an agent getting infected depends on their neighbor's infection status, their susceptibility, and a parameter that represents the effective contact rate. We construct the neighborhood based on household and mobility data from the U.S. Census. For the labor market, we use an econometric model that connects individual willingness to work with the overall unemployment rate, factoring in historical unemployment claims. We assess the model's performance against real data using 3 types of agent architectures: heuristic, archetype, and LLM agents. Heuristic agents follow the basic equations, while archetype and LLM agents modify these equations to include decisions influenced by LLM outputs regarding isolation and work. During the simulation, we sample agent decisions at each step to track infection and unemployment rates over time. Notably, for LLM and archetype agents, the contextual information comes from the simulation itself rather than external data, allowing for prospective analysis. While AgentTorch can efficiently simulate the entire population with archetypes, it requires subsampling for LLM agents. We calibrate the structural parameters to match historical data on infections and unemployment. We initialize each ABM with its respective agent type and use AgentTorch's features for calibration, employing gradient-assisted techniques. After calibration, we simulate future infection and unemployment data and compare it with independent validation data. Our results show that the archetype model performs best, emphasizing the importance of adaptive agents and simulating the full system scale. We also analyze simulation dynamics with AgentTorch, which allows us to evaluate past measures, explore hypothetical scenarios, and design future interventions. For instance, we assess the impact of stimulus payments on employment behavior at a neighborhood level, demonstrating how our model can address the limitations of historical data in policy design. In counterfactual analyses, we examine the effects of pandemic fatigue and variant transmissibility by simulating different scenarios, such as the emergence of the Delta variant later in the pandemic and adjusting transmissibility parameters to reflect the Omicron variant. Finally, AgentTorch enables us to design targeted interventions by analyzing demographic behaviors, helping policymakers allocate resources effectively. We validate two intervention strategies: distributing rapid tests during high mobility periods and delaying second vaccine doses for certain demographics when supply chains are critical.